हेलो फ्रेंड्स। तो आज में आपका स्वागत। हमने स्टार्ट किया है 11th क्लास की एनसीईआरटी की सीरीज, जिसमें हमने स्टार्ट किया है केमिस्ट्री। तो हम स्टार्ट करते हैं 11 यूनिट हमारा पी ब्लॉक ऑफ पी ब्लॉक एलिमेंट्स। P block elements on the last electron touch the outermost p orbital. As we know that the number of p orbitals is 3, and therefore the maximum number of electrons that can be accommodated inside of p orbital is 6. Consequently, there are 6 groups of p block elements in the periodic table, numbering from 13 to 18. Boron, carbon, nitrogen, oxygen, fluorine, and helium lead ahead the groups. Now, their valence shell electronic configuration is NS3 and P126, except for helium. The inner core of the electronic configuration may, however, differ. The difference in an inner core of elements greatly influence their physical properties, such as atomic properties. Consequently, a lot of variation in properties of elements in a group of p block is observed. The maximum oxidation state shown by the p block element is equal to the total number of valence electrons, that is the sum of the s and p or electrons. Clearly, the number of possible oxidation states increases towards the right of the periodic table. In elements, they may show other oxidation states which normally elect but not necessarily differ from the total number of valence electrons by unit of 2. The important oxidation states exhibited by p block elements are shown in table 11.1 in exhibited now. In boron, carbon, and nitrogen the group of oxidation states the most stable state for the lighter elements in the group. However, the oxidation state 2 unit less than the group oxidation state becomes progressively more stable for the heavier elements in each group. The occurrence of oxidation states 2 units less than the group oxidation states are sometimes attributed to the inert pair effect. The relative stabilities of these two oxidation states, group oxidation state and 2 units less than the group oxidation state, may vary from group to group and will be discussed at appropriate places. It is interesting to note that the non-metals electrolytes exist only in the p block of the periodic table. The non-metallic character of the elements decreases down the group in fact, the heaviest element in each p block group is the most metallic in nature, and this change from non-metallic to metallic character brings diversely in the chemistry of these elements depending on the group to the which they belong. In non-metals have a higher ionization enthalpies and higher electronegativities than the metals. Hence, in contrast to metals, which anions the compounds formed by highly reactive nonmetals with highly reactive metals in their electronegativities. On the other hand, compounds formed between nonmetals themselves are largely covalent in character because of small differences in their electronegativities. The change of nonmetallic and two metallic character can be best illustrated by the nature of oxides they form. The non-metal oxides are acidic and neutral, whereas metal oxides are basic in nature. The first member of a block differs from the remaining members of their corresponding group in two major respects. First is the size and all the other properties which depend on size. Thus, the lightest p block elements show the Same kind of differences as the lightest s block elements, lithium and beryllium. The second p block element arises from the effect of d orbitals in the valence shell of heavier elements, starting from the third period outward onwards, and their lack of second period elements. The from boron are restricted to the maximum covalence of 400 using 2s, and there are 3 2p orbitals in contrast. Now, the third period elements of group p groups with the electronic configuration 3s2 3pn have the vacant d3 orbital lying between 3p and the levels of energy. Elements can be expanded their covalence above 4. For example, while boron forms only BF4 negative aluminum gives ALF the 6 trinegative ion. The presence of this d orbitals influences the of the other waves. The combined effect of size and availability of d electrons, d orbitals considerably influences the ability of these elements to form pi bonds. The first member of a group differs from the heavier members in its ability to form pi multiple bonds to itself, that is carbon carbon double bond and carbon carbon triple bond, nitrogen nitrogen double bond, and so to other second row elements. Example: carbon oxygen double bond, carbon nitrogen double bond, carbon nitrogen triple bond, nitrogen oxygen double bond. This type of pi bonding is not particularly strong enough for the heavier p block elements. The heavier elements do form pi bonds, but this involves d orbitals pi and d pi, as the d orbitals are of higher energy than the v orbitals. They contribute less to the overall stability of molecules than does p pi bonding of the second row elements. However, the coordination number of species of heavier elements may be higher than for the first element in the same oxidation state. For example, in +5 oxidation state, both An and P form on oxoanions. NO3 negative 3 coordination with pi bonds involving one per nitrogen p orbital, and PO4 trinegative for 4 coordination involving s, p and d orbitals, contributing to the pi bonds. In this unit, we will study the chemistry of group 13-14 elements of the periodic table. Group 13 elements, the boron family. The group element show a wide variation in properties. Boron is a typical non-metal. Aluminum is a metal but shows many chemical similarities with boron, and gallium, vanadium, and thallium, and most exclusive metallic in character. Boron is a fairly rare element, mainly orthoboric acid, H3BO3, borax, Na2B4O7, Na.10 times H2O, carnite, Na2B4O2, dot 4 times H2O. In India, borax occurs in Puga Valley, Ladakh. Abundance of boron in Earth crust is less than 0.0001% by mass, and there are two isotopic forms of boron, B10 and B11. Aluminum is the most abundant metal and the third most abundant element in the Earth's crust, 8.3% by mass, after oxygen 45.5%, and silicon 27.7%. Bauxite, Al2O3, dot 2 times H2O, and cryolite. Na3 of AlF6 are the important minerals of aluminium. In India, it is found as mica in Madhya Pradesh, Karnataka, Orissa, and Jammu Gallium. Indium and thallium are less abundant elements in nature. Nithonium Nihonium has a symbol NH, atomic number 113, atomic mass of 286 gram per mole, and electronic configuration Rn. 5 of 14 and 6d10 7s2 7p2. So far it has been prepared since small amount, and half life of its most stable isotope is 20 seconds. Due to these reasons, its chemistry has not been established. Nahonium is a synthetically prepared reactant. Here, atomic, physical, and chemical properties of elements of this group living on lithium are discussed below. Electronic configuration. The outer electronic configuration of these elements is NS2 and P1. The close look at the electronic configuration suggests that while boron and aluminum have noble gas core, gallium and indium have noble gas plus 10 d electrons. The thallium has noble gas plus 14 of electrons plus 10 d electrons cores. Thus, the electron structures of these elements are more complex than for the first two groups of the elements discussed in Unit 10. This difference in electronic structures affects the other properties and consequently the chemistry of all elements of this group. On moving down for each successive member, an extra share of electrons is added, and therefore atomic radius is expected to increase. However, deviation can be seen. Atomic radius of gallium is less than that of aluminium. This can be understood from the variation in the inner core of the electronic configuration. The presence of additional 10d electrons offer only post-scaling effect. The unit 2 for the outer electrons from the increased nuclear charge in gallium. Consequently, the atomic radius of gallium is less than that of the aluminium. Ionization enthalpy. The ionization enthalpy values are expected from the general trends do not decrease smoothly down the group. The decrease from B to boron to aluminium is associated with increase in size. The observed discontinuity in the ionization enthalpy values between aluminum and gallium and between the indium and thallium are due to inability of D and F electrons, which have a low screening effect to compensate the increase in nuclear charge. The other order of ionization enthalpies as expected is delta H. Delta H1 is less than delta H2 is less than delta H3. The sum of the first three ionization enthalpies for each of the elements is very high. The effect of this will be apparent when you study their chemical properties. Electronegativity. Now down the group, electronegativity first decreases from boron to aluminum and then increases marginally. This is because of the discrepancies in atomic size of the elements. Physical properties. Boron is non-metallic in nature. Now it is extremely hard and black colored solid. It exists in many allotropic forms due to very strong crystalline lattice. Boron has a unusually high melting point. The rest of the members of are soft metals with low melting point and high electrical conductivity. Now it is worthwhile to note that gallium with unusually low melting point 303 Kelvin could exist in liquid state during summer. Mm, its high boiling point 2676 Kelvin makes it a useful material for measuring high temperatures. Density of the elements increases down the group from boron to thallium. Chemical properties, oxidation state, and trends in chemical reactivity. Due to small size of boron, the sum of its first three ionization enthalpies is very high. This prevents it to from form plus 3 ions and forces it to form only covalent compounds. But as we move from boron to aluminum, the sum of the first three ionization enthalpies of aluminum considerably decreases, and now is therefore able to form aluminum tripositive ions. In fact, aluminum is a highly electropositive metal. However, down the group, due to poor shielding effect of intervening d and f orbitals, the increased effective nuclear charge holds ns electrons tightly responsible for inert pair of effect, and thereby restricting their participation in bonding. As a result of this, only p orbitals electrons may be involved in bonding. In fact, in gallium and thallium, both 1 plus 1 and stability of plus 1 oxidation state now progressively increase for heavier elements, and thallium is greater than indium is greater than gallium is greater than aluminum. In thallium, plus 1 oxidation state is predominant, whereas the plus 3 oxidation state is highly oxidizing in character. The components in the plus 1 oxidation state, as expected from energy considerations, are more ionic than those in the plus 3 oxidation state. In trivalent state, the number of electrons around the central atom in a molecule of the compounds of these elements, example boron in BF3, will be only 6. Such electron deficient molecules have tendency to accept a pair of electrons to achieve stable electronic configuration, and thus behave as Lewis acids. The tendency to have the Lewis acid decreases with the increase in the size down the group. BCl3 easily accepts a lone pair of electrons from ammonia to form BCl3 NH3 tetrahedral. In trivalent state, most of the compounds being covalent are hydrolyzed in water. For example, the trichlorides on hydrolysis and water form tetrahedral MOH4 species. The hybridization state of element M is sp3. The aluminum chloride is in the acidified aqueous solution forms octahedral LH2O sometimes plus the positive ion, and this complex ion the 3d orbitals of aluminum and involves the hybridization state of aluminum is sp3d2 problem 11.1 standard electrode potential values E for aluminum tripositive aluminum is minus 1.66 volt, and that of titanium tripositive is plus 1 0.26 volt. Predict about the formation of M tripositive ion in solid solution and compare the electropositive character of the two metals solution. Standard electrode potential values for two half cell reactions suggest that aluminum has high tendency to make aluminum tripositive ions, whereas titanium tripositive is not only unstable in solution but is a powerful oxidizing agent. Also, the titanium tripositive is more stable in solution than titanium tripositive. Aluminum being able to form tripositive ions easily is more electropositive than thallium. Reactivity towards air. Now, boron is unreactive in crystalline form. Aluminum forms a very thin oxide layer on the surface which protect the metal from further attack. Amorphous boron and aluminum metal on hitting in air form B2O3 and Al2O3 respectively. With dinitrogen at high temperature, they form nitrides. 2 times C solid plus 3 times O2 then gives 2 times C2O3. 2 times C plus N2 then gives 2 times Cn. is element. The nature of these oxides varies down the group. Boron trioxide is acidic and reacts with the basic metallic oxides, forming metal of borates. Aluminum and gallium oxides are amphoteric, and those of indium and thallium are basic in their properties. Reactivity towards acid and alkalis. Boron does not react with the acids and alkalis even at moderate temperature, but aluminum dissolves in mineral acids and aqueous alkalis and thus shows amphoteric character. Aluminum dissolves in dilute HCl and liberates hydrogen 2 times Al plus 6 times HCl, then gives 2 times Al tripositive plus 6 times Cl negative plus 3 times H2. However, concentrated nitric acid renders aluminum passive by forming a protective oxide layer on the surface. Aluminum also reacts with aqueous alkali and liberates dihydrogen 2 times aluminum plus 2 times NaOH plus 6 times H2O, then gives 2 times Na positive, AlOH 4 times N negative plus 3 times H2 gases. Reactivity towards halogen. These elements react with halogens to form tetrahalides except TiAl3. Problem 11.2. White fumes appear around the bottle of anhydrous aluminum chloride. Give reason. Solution. Anhydrous aluminum chloride is partially hydrolyzed with atmospheric moisture to liberate HCl gas. Moist HCl appears white in color. Important Important trends and anomalous properties of boron. Certain important trends can be observed in the chemical behavior of group 13 elements. The trichlorides, bromides, and iodides of all these elements, being covalent in nature, are hydrolyzed in water. Species like tetrahedral MOH4 negative and octahedral MOH2 6 times tripositive, except in boron, exist in aqueous medium. The monometric trihalides, being electron deficient, are strong Lewis acids. Boron trifluoride easily reacts with the Lewis bases such as NH3 to complete octet around boron. F3b plus NH3 then gives F3b NH3 it is due to the absence of d orbitals. That d orbitals are available with aluminum and other elements. The maximum covalence can be expected beyond 4. Most of the other metal halides, the LCl3, are dimerized through halogen breaking. Now the Al2Cl6. Now the metal species completes its octet by accepting electrons from halogen and the halogen bridged molecules. Problem 11.3. Boron is unstable to form a BF6 negative ion. Explain. Solution. Due to non-availability of d orbitals, boron is unable to expand its octet. Therefore, the maximum covalence of boron cannot exceed 4. Some important compounds of boron. Some useful compounds of boron are borax, orthoboric acid, and diboron. We will briefly study their chemistry. Borax, it is most important compound of boron. It is a white crystalline solid of formula Na2B4O7 dot 10 times H2O. In fact, it contains the tetranuclear units B4O5 OH 4 times negative, and correct formula therefore Na2B4O3 OH 4 times dot 8 times H2O. Borax dissolves in water to give an alkaline solution Na2B4O7 plus 7 times H2O, then gives 2 times NaOH plus 4 times H3BO3 orthoboric acid. On hitting borax, first loses water molecules and swells up. On further heating, it turns into a transparent liquid which solidifies into glass-like material known as borax bed. Na2b4o7 dot 10 times H2O. In presence of heat then gives Na2b4o2o7 in presence of heat then gives 2 times NaBO2 plus B2O3. The metaborates of many transition metals have characteristics, colors, and therefore borax braid test can be used to identify them in the laboratory. For example, when borax is heated in the one burner, a flame with a COO on a loop of platinum wire, the blue colored CO, BO2, O2, 2 times. Now, here bead is formed orthoboric acid. Orthoboric acid H3BO3 is a white crystalline solid with a soapy touch. Now it is sparingly soluble in water but highly soluble in hot water. It can be prepared by acidifying an aqueous solution of borax Na2b4o7 plus 2 times HCl plus 5 times H2O then gives 2 times NaCl plus 4 times B in bracket OH 2 times. It is also formed by the hydrolysis reaction with the water or dilute acid of most boron compounds, halides, hydrides, etc. It has a layer structure in which planar BO3 units are joined by hydrogen bonds as shown in figure. Boric acid is a weak monobasic acid. It is not a protonic acid but acts as a Lewis acid by accepting electrons from a hydroxyl ion BOH3 plus 2 times HOH then gives to BOH 4 times negative plus H3O positive. The on heating orthoboric acid above 370 Kelvin forms metaboric acid HBO2 which on further heating yields boric oxide B2O3. Structure of boric acid. Um, the dotted lines represent hydrogen bonds. Problem 11.4. Why is boric acid considered as a weak acid solution? Because it is not able to release hydrogen H positive ions on its own. It receives OH negative ions from water molecule to complete its octet and in turn releases H positive ion. Diboron H2B6. The simplest boron hydride known as diboron. It is prepared by treating boron trifluoride with LiAlH4 as diethyl ether. 4 times BF3 plus 3 times LiAlH4 then gives 2 times B2H6 plus 3 times LiHAlF plus 3 times AlF3. Now, convenient laboratory method for the preparation of diboron involves the oxidation of sodium borohydride with the iodine 2 times NaBH4 plus I2 and then gives and then gives to B2 plus B2H6 plus 2 times NaL plus H2. The diboron is produced on an industrial scale by the reaction of BF3 with sodium hydroxide 2 times BF3 plus 6 times NaH in presence of 450 Kelvin B2H6 plus 6 times NaF. Diboron is a colorless, highly toxic gas with the ABP of 180 Kelvin. Diboron catches fire spontaneously upon exposure to air. It burns in oxygen, releasing an enormous amount of energy. Most of the higher borages are also spontaneously flammable. In here, boranes are readily hydrolyzed by water to give boric acid, and diboron undergoes cleavage reactions with Lewis bases to give boron products adducts BH3L reaction of ammonia with diborane gives initially B2H6 dot 2 times NH3, which is formulated as B2BH2 NH3 2 times positive, BH4 negative. Further heating it gives borazine B3N2H6, known as inorganic benzene, in view of its ring structure with alternate BH and NH groups. B2H6 plus 6 times NH3, then gives 3 times BH2, NH3 2 times, and positive, BH4 negative, then gives 2 times B3 and 3 on UH6 plus on 12 times as CH2. The structure of diborane is shown in the figure 11.2. The figure, the four terminal hydrogen atoms and the two boron atoms lie in the one plane above the above and below this plane. Now there are two bridging hydrogen atoms. Now the four terminal BH bonds are regular two center two electrons bonds, while the two bridge BHB bonds are different and can be described in terms of three. The structure of diborane BH6: center two electron bonds shown in figure 11.2b. Boron also forms a series of hydroborates. Now, the most important one is the tetrahedral BH4 ion hydroborates of several metals are known. The lithium and sodium tetrahydroborates, also known as borohydrides, are prepared by the reaction of metal hydrides with B2H6 is diethyl ether 2 times MH plus B2H6, then gives 2 times M positive, BH4 negative. 11.2b bonding in diborane, and both LiBH4 and NaBH4 are used as reducing agents in organic synthesis. They are useful starting materials for preparing other metal borohydrates. Uses of boron and aluminium and their compounds. Boron being extremely hard refractory, a solid of a high melting point, low density, and very low electrical conductivity, finds many applications. Boron fibers are used in making bulletproof vest and light composite material for aircraft. The boron 10 isotope has a high ability to absorb nucleic acid neutrons, and therefore metal borides are used in nuclear industry as a protective shields and control rods. The main industrial application of borax and boric acid is in the manufacture of heat resistant glasses. Example: Pyrex, glass wool, and fiberglass. Borax is also used as a flux for soldering the metals for heat, starch, and stain resistant glazed coating to earthenwares as constituent of medicinal soaps, and an aqueous solution of orthoboric acid is generally used as a mild antiseptic. Aluminium is a bright silvery white metal and high tensile strength. It has a high electrical and thermal conductivity on a weight to weight basis. The electrical conductivity of aluminium is twice that of the copper. Aluminium is used extensively in the industry and everyday life. It forms alloys with copper, magnesium, zinc, manganese, silicon, and silver, silicon and zinc. Aluminium and its alloys can be given shapes of pipe, tubes, rods, wires, plates, and foils, and therefore find uses in packing utensils, making industry. The use of aluminium and its compounds for domestic purposes is now reduced considerably because of their toxic nature. Group 14 elements, the carbon family: carbon, silicon, germanium, the tin, lead, and VM are the members of group 14. Carbon is the 17th most abundant element by mass in the Earth's crust. Now it is widely distributed in nature in free as well as in the combined state. In elemental state, it is available as coal, graphite, and diamond. However, in combined state, it is present as metal, carbonates, and hydrocarbons and carbon dioxide gas 0.03% in air. One can emphatically say that carbon is the most versatile element in the such as hydrogen, dihydrogen, dioxygen, chlorine, and sulfur provides as an astonishing array of materials ranging from living tissues to drugs and plastics. Organic chemistry is devoted to carbon containing compounds. It is an essential constituent of all living organisms. Naturally occurring carbon containing two stable isotopes, C12 and C13. Now, in addition to this, third isotopes, C14 is also present. It is a radioactive isotope with half-life 5,770 years and used for radiocarbon dating. Silicon is the second to 27.7% kilogram of mass, most abundant element on the Earth's crust and is present in nature in the form of silica and silicates. Silicon is a very important component of ceramics, glass, and cement. Germanium exists only in traces. Tin occurs mainly as cassiterite, essence O2, and lead has galena, PBS, fluoro. Flerovium is synthetically prepared radioactive element. Ultra pure form of germanium and silicon are used to make transistors and semiconductor devices. A symbol of flerovium is Fl. It has atomic number 114, atomic mass of 289 gram per mole, and electronic configuration Rn of 5f14 6d10 7s2 7p2. It has been prepared only in small amount. Its half life is short and its chemistry has not been established yet. The important atomic and physical properties along with their electronic configuration of the element of group 14 leaving flerovium are given in table 13 by 11.3. Some of the atomic physical and chemical properties are discussed below. Electronic configuration: the valence shell electronic configuration of these elements is ns2 and p2. The inner core of the electronic configuration of elements in this group also differs. Covalent radius: there is a considerable increase in covalent radius from carbon to silicon. Thereafter, from silicon to lead, a small increase in radius is observed. This is due to the presence of completely filled d and f orbitals in heavier members. Ionization enthalpy: the first ionization enthalpy of group 14 members is higher than the corresponding members of group 13. The influence of inner core electrons is visible here also. In general, the ionization enthalpy decreases down the group. Small decreases in delta H from silicon to germanium to sandium, and slight increases in delta H and from the SN to PL lead is the consequence of poor shielding effect of intervening d and f orbitals and increase in size of the atom. Electronegativity: due to small size, the elements of this group are slightly more electronegative than group 13 elements. The electronegativity values of for elements from silicon to lead are almost the same. Physical properties: the members of group 14 are solids, carbon and silicon are non-metals, germanium is metalloids, and whereas tin and lead are soft metals with low melting points. Melting points are boiling and boiling points of group 14 elements are much higher than those of corresponding elements. So group 13. Chemical properties: oxidation states and trends in chemical reactivity. The group 14 elements have four electrons in outermost shell. The common oxidation states exhibited by these elements are +4 and +2. Carbon also exhibits negative oxidation states since the sum of the first four ionization enthalpies is very high. Compounds in four oxidation state are generally covalent in nature. And heavier members of the tendency to show +2 oxidation state increases in the consequence of lead is greater than tin is greater than germanium. It is due to the inability of the NS2 electrons of valence shell to participate. Reactivity towards oxygen, reactivity towards water, reactivity towards halogen. Important trends and anomalous behavior of carbon. Allotropes of carbon, diamond, ग्राफाइट, फुलेरिन्स. कुछ स्ट्रक्चर है, डायमंड का स्ट्रक्चर दिया हुआ है यहाँ पर, ग्राफाइट का स्ट्रक्चर दिया हुआ है, एंड देन फुलेरिन का स्ट्रक्चर दिया हुआ है. यूजेस ऑफ कार्बन, सम इम्पोर्टेंट कंपाउंड्स ऑफ कार्बन एंड सिलिकॉन. कार्बन डाइऑक्साइड, silicon dioxide as SiO2, silicons, silicates and zeolites. Then summary है P block की. P block of the periodic table is unique in terms of having here gives of elements, metals and non-metals and metallites. There are 6 groups of P block elements in the periodic table, numbering from 13 to 18. Their valence shell electron configuration is ns2 and p1 to 6. Now, influence their physical and chemical properties. As a consequence of this, a lot of variation in the properties among these elements is observed. In addition to the group oxidation state, these elements show other oxidation states differing from the total number of valence electrons by units of 2. While the group oxidation state is the most stable for the lighter elements of the group, lower oxidation states becomes progressively more stable for the heavier elements. The combined effect of size and availability of d orbitals considerably influences the ability of these elements to form pi bonds, while the lighter elements form pi bonds. The heavier ones form d pi and d pi bonds. The absence of d orbitals in the second period elements limits their maximum covalence to 4, while heavier ones can exceed this limit. Boron is a typical non-metal and the other members are metals. The availability of 3 valence electrons 2s2 3p2p1 for a covalent bond formation we were using four orbitals 2s 2p 2py and 2pz leads to the so-called electron deficiency in boron compounds. This deficiency makes them good electron acceptor and thus boron compounds behave as Lewis acids. Boron forms covalent molecular compounds with a dihydrogen as boranes, the simplest of which is diboron B2H6. Diboron contains two bridging hydrogen atoms between two boron atoms. So these bridge bonds are considered to be 3 center 2 electron bonds. BOH 2 times 3 times is a weak monobasic acid. It acts as a Lewis acid by accepting electrons from bond test gives characteristic colors of transition metals. Aluminum exhibits oxidation states with heavier elements. So +1 oxidation state gets progressively stabilized on going down the group. This is a consequence of the so-called inert pair effect. Carbon is a typical non-metal forming covalent bonds employing all its 4 valence electrons 2s2 to p2. It shows the property of catenation, the ability to form chains or rings not only with carbon-carbon single bond but also with multiple bonds, carbon-carbon double bond, carbon-carbon triple bond, and the And the best example of allotropy. Now, three important allotrophs are of carbon are diamond, graphites, and fluorine. The members of the carbon family mainly exhibit +4 and +2 oxidation states. The compounds is +4 and +4 oxidation states are generally covalent in nature. The tendency, whereas +4 oxidation state it is a strong oxidizing agent. A carbon also exhibits negative, whereas CO2 is acidic in nature. Carbon monoxide having a lone pair of electron on carbon complex as compared to that of oxohemoglobin complex. The carbon dioxide as such is not, and decomposition of limestone is feared to cause increase in greenhouse effect. This in turn raises the temperature of the atmosphere and causes serious complications. Silica, silicates, and silicones are important glass of compounds and find applications in industry and in technology. तो यहाँ पर भी ब्लॉक ऑफ एलिमेंट्स ख़त्म होता है. यहाँ पर हमने पहले से देखा, कुछ इंपॉर्टेंट पॉइंट्स देखे. Group 13 family, Group 14 family, chemical properties, physical properties, important traits of anomalous, diborane. Group 14 elements, carbon, electron configuration, electronegativity, reactivity, डायमंड, ग्राफाइट, फ्लोरीन. इसके स्ट्रक्चर देखें, ये बहुत ज़्यादा इंपॉर्टेंट है. इसके स्ट्रक्चर, सिलिकेट्स एंड जियोलाइट देखें, देन समरी देखें. प्लीज़ इस वीडियो को ज़्यादा से ज़्यादा शेयर कीजिएगा. प्लीज़ लाइक, शेयर एंड सब्सक्राइब. थैंक यू सो मच फॉर वॉचिंग.